the invitation. Thanks so much for the invitation, the kind introduction. I wanted to tie together several projects I'm working on under this theme of new massively parallel array coils for extending the reach of MRI and also TMS to show what we can do when we improve our instrumentation, provide more degrees of freedom for either detecting or shaping fields in the body as a way of augmenting our MRI scanners. So I'm going to try to motivate the need for better coils by talking about mesoscale brain imaging. And what can we do to improve our sensitivity in MRI and acquisition speed without changing out the magnet itself? Because of course you get more SNR at higher field strengths, but given that you have an existing magnet, 3T, 7T, how can you achieve its full potential? And I'm going to argue we're not there yet. We need better hardware to work with the scanner, especially array coils. I'm also going to show that once you have an array of independently controlled coils, you can use them not only for signal detection, but also for field shaping. And we're exploring some new uses of local field control and that I'm going to talk about. And this is a very active area where I'd love to get feedback on new applications and new ideas. And then I'm going to show how not only for imaging, but also neuromodulation, we can benefit from having more degrees of freedom in our array, and how we can tie in TMS with MRI. So general theme is better instrumentation. This has always been important in science, right? Maybe the most famous example is, why did Galileo see further? It's because he had better telescopes. And you can see some, amazing drawings he made of the moon in 1609, that he was able to simply see more than his contemporaries. And that's one reason he was such an impactful scientist. If you then look to the modern era, of course, we have the Hubble Space Telescope, which gives us these absolutely incredible deep field images that Galileo could scarcely imagine in his day, right? So, almost 400 years later, we've made incredible strides. And now, of course, the latest space telescope is the James Webb. And very, very exciting, just in the last month or so, we're started to see images come off this new instrument. And you just see the amazing improvements in resolution and sensitivity compared to previous infrared telescopes. So obviously super exciting. We'll see where James Webb goes in the coming years. But how does this tie in with imaging? Well, since Hubble launched in 1990, MRI has also come a long way. And if you look at structural images, here's an example of where we were state-of-the-art in 1991. And here's where we were circa 2010 for 7 Tesla structural imaging, where you start to approach the limits of what you can do given that the person is moving, and there's physiological processes that cause blurring and ghosting, et cetera. At this point, those physiological confounds start to become the main barrier to further improvements in voxel size. But this is 300 micron in plane. So in addition to anatomical imaging, of course, we're very interested in functional imaging. And this has also come a really long way since the time that Hubble was launched. So if you look at some of the original fMRI papers, very impressive for the time, but you're still looking at these pretty, diffuse blobs on the brain. This was Jack Beliveau using exogenous contrast, and then Ken Kwong using endogenous contrast for some of the early bold experiments here at the bottom. And of course, just a reminder, bold is giving us subtle changes in T2 star modulation of our EPI image, which we can then correlate to the fraction of hemoglobin that's oxy versus deoxy. And this oxy to deoxy hemoglobin fraction, of course, changes when there's brain activity. And we can then use this as an indirect way to study brain circuits. But then look at today, this is work from Renzo Huber done at 7 Tesla with the VASO technique, where you start to zoom in on somatosensory cortex and you see individual digits mapped onto the brain, either for sensory or motor scans. Really impressive improvements from the diffuse blobs we would see in the visual area in 1990. So here's an example of what the EPI looked like in 1990 versus today. This is a 25 millimeter slice. If you go now to a 1 millimeter isotropic resolution scan, which you can do on any 7T, you're looking at about 200 times smaller voxel. So I think really dramatic improvement, and this is enabling us to study the architecture of the cerebral cortex in much finer detail. But I'm going to argue we still need better than 1 millimeter. Why do I care about going below 1 millimeter? Well, if you look at the organization of the cortex, of course, there are layers. And those layers here, I'm superimposing on voxels. Here is about a 1 millimeter voxel. And then this is what we're calling next gen 7T, which is driving down toward 0.5 millimeter voxels for functional imaging. And this is really important because now you can begin to resolve individual layers of cortex. And we think that the different layers may play a different role in information processing. And if you look at visual cortex, of course, you have ocular dominance columns, and then you have patches of cortex, which have been imaged with other methods invasively, showing a preferential sensitivity to bars at different orientations. This, is still too small to be resolved with state-of-the-art 7T MRI, but we're getting very close. And so this has some tie-in also to brainstem imaging. It's not just the cortex where we care about resolution. I have a K99 grant where we're interested in doing functional imaging of subcortical circuits to see how they play a role in arousal and how this role is disrupted in anesthesia. And just to cut to the punchline, our existing resolution is just not good enough to see functional activity in structures like the locus coeruleus and these small, thalamic nuclei, et cetera. So to test a hypothesis about the mechanism of action of anesthesia, we still need better resolution in our fMRI. So if we follow this theme of NASA's great observatories, including the Hubble, could we have great observatories for studying brain architecture and function? They could perhaps be shared instruments where we really push the SNR and the CNR at 7T and above to study the brain in finer detail. And indeed, we do need higher channel count arrays to fully unlock the potential of these instruments for improving signal detection and boosting accelerated imaging performance. And as I'm going to argue, improving our ability to locally control the magnetic field for shimming. And so one example of such an instrument is the UC Berkeley 7T MRI corticography magnet. This magnet is now up and running and is part of a big collaboration that includes Siemens and also MGH, and has boosted gradient performance as well as state-of-the-art radiofrequency coils, and will have state-of-the-art shims. And we're part of the collaboration to supply instrumentation for this scanner. So if you compare it to a conventional 7T, it's got about 3 times the Gmax and over 4 times the max slew rate. And it also has 128 receive channels and will eventually have higher order shims as well. And so what's so exciting about this is that you may be approaching the sensitivity limits of 7T fMRI with this combination of hardware. You would no longer be spatial encoding limited, meaning it's your gradients and your coils that are limiting you from hitting your resolution limit. We want to drill down to the fundamental limits that are supported by the SNR available at 7T and not be spatially encoding limited. And the other cool thing about this is that if you boost your gradient slew rate, you can reduce your echo spacing in MRI. That reduces your distortion. And with more receive channels, you can also have better parallel imaging performance, which gives you a multiplicative benefit to distortion. So if you boost your parallel imaging by a factor 2 and your gradient performance by a factor 2, you get a factor of 4 in distortion reduction. And then by further adding multi-coil shimming, we hope to reduce distortion by reducing the baseline off resonance, as I'll show later in the talk. So to motivate this, what are RF arrays and why do we need them? Array coils have been around since 1990, shown in this paper by Romer and Edelstein. They extend coverage over the anatomy of interest, and they have independently detected signals from inductively decoupled loops in an array. And by patterning the arrays close to the body, you improve SNR by improving the loading of the coil so that it's body noise dominant. And this has been extended to helmets for brain imaging. This is a 32-channel array from Larry Wald and Graham Wiggins from 2005, showing that you get very nice independent measurements of the signal over the brain, if you see, from the different coils patterned on this helmet. And this buys you quite a boost in SNR at the same field strength. So you can see overlaying an 8 and 32-channel array coil compared to a volume circularly polarized coil, you get a huge benefit in SNR, especially toward the edges of the field of view. And you can do more than that. You get more than just an SNR boost from these coils. You can also do parallel imaging using methods such as SENSE that you may be familiar with, where you can undersample case space and get an aliased image on each coil. But by using the independent spatial sensitivities of the different coils, you piece these back together into a full field of view image. And the more channels you have in your array, the better the conditioning of this image reconstruction problem becomes. The conditioning is usually described as a G factor or geometry factor, which tells you how much the noise will be amplified in the final image. And it depends on how many array coils are available to you. And here you just see a dramatic improvement going from 8 to 32 channels. So how many channels is enough? And when should we stop? Well, one way of addressing this question is to look at what's called the Q ratio, which varies as a function of loop diameter for a typical standoff distance from the body. And loading typically increases at high field. So at 7T, you get a better Q ratio. It tells you how sample or body noise dominated you are versus copper noise dominated inside the coil. And this is important because if you're not body noise dominated, you are probably not going to have the best achievable SNR for your array. So you typically, the smaller the loops are, the closer you need to be to the body. And it also works better at high field. So if you look at a typical loop diameter for 32 channel, you still are body noise dominated at 3T and 7T. But as you push toward 128 channel with the smaller loop diameter, it wouldn't make sense to do this at 3T because you'd now be dominated by the copper losses in the coil rather than the sample noise from the body. Whereas at 7T, these bench measurements suggest we still have a net win by building a 128 channel array at 7T. So you can then do calculations of the ultimate achievable SNR. Here we're showing a simplified case of a sphere with loops patterned around the sphere. And what we want to know is if you could have a perfect detector array on this sphere with no losses whatsoever in the copper, what would be the best possible SNR you could get inside your sample? And what we see in these simulations from NYU is that the more loops you add, the closer you get to the best achievable SNR in this sample. And the reason you get better is because you can better approximate the current distribution on the surface that gives you optimal B fields and E fields in the sample for optimizing sensitivity while minimizing loss. So there are a continuously varying sheet of current on this sphere that would give you the best possible SNR. And the more loops you add, the closer the currents in those loops can approximate that optimal distribution. So with these simulations as motivation, we went ahead and built a 128 channel receiver array for the UC Berkeley scanner. You can see here the layout of the loops on the helmet, and then the final coil, which is now at UC Berkeley for testing. And we compared it with 32 and 64 channel coils, and indeed saw that the SNR scales, as our simulations suggest. Most of the benefit is at the periphery, as you can see from this 1D line plot. But it agrees with our simulations done using Marie fast integral equation solver, which show the same trend of boosted performance near the periphery. So we do indeed get a benefit going to a higher channel count array. And we not only win in SNR, but you also win in G factor. So here, if you look at these highly accelerated cases for R5, R5, R6 in plane undersampling or twofold undersampling, here shown at right, going from a 32 channel to a 128 channel array, you get a big win. If you were to do R6 undersampling, you'd only have 40% retained SNR with the 32 channel array. You'd have 72% average retained SNR with the 128 channel. So that's a real game changer for these highly accelerated acquisitions. And likewise, if you go to 2D or multi-band acquisitions, you see the same trends. You really do get a benefit from having more independent degrees of freedom around the brain for the parallel imaging reconstruction. So what's the next step? Well, these arrays are very dense with low noise amplifiers and with cables, and it becomes very challenging to build so many channels close to the head. So the question then is, how do you make this more manufacturable? And one idea is to build an ASIC that includes all the RF front-end components in a small package that's easier to build, has less power dissipation, takes up less space. And maybe you want to move away from coaxial connections on the output of the preamps and use fiber optic relays with a built-in ADC. There are ways that the RF could be streamlined. But in addition to this, there's a way to use this array for more than just RF signal reception. As I'll show, you can make it usable for B0 shimming as well. And so what is B0 shimming? Why do we care? Well, if you look at field maps at 7 Tesla, the field magnetizes materials in the body, particularly the oxygen in the sinus cavities. And this paramagnetic field source creates perturbations in the field inside the brain, which lead to off-resonance artifacts in a variety of MRI acquisitions. And this is a very significant problem, especially at 7 Tesla. So if we're trying to do a T2 star sensitive methods such as bold fMRI or SWI, the microscopic T2 star of the tissue can be confounded by the macroscopic T2 star variations caused by these overlaying B0 fields. And this gets worse at the higher field strengths. So one effect of shortening the T2 star is that you have very pronounced signal voids, especially in these gradient echo slices shown here. It does get better as you move to a thinner slice, but you're still going to have some reduction in T2 star and some loss of signal. You also get geometric distortion in your EPI. So here I'm showing that as you go from 3T to 7T for the same EPI parameters, you get a lot more geometric distortion in these slices, especially in like the frontal lobes. This makes it harder to register your EPI to an anatomic reference. And it's hard to fully correct for this in post-processing. So there are ways to mitigate EPI distortion, for example, going to a stronger gradient coil, as they did at UC Berkeley, and using parallel imaging with your array coil to reduce the effective echo spacing. That helps, but it never fully fixes the problem. And so by eliminating B0 inhomogeneity at the source, you might be able to mitigate this and still take advantage of parallel imaging and gradient, better gradient coils to have multiplicative gains by using all three methods together. So what is B0 shimming? Well, you know, in Boston here with all these old buildings, the floor usually looks like this. So when you build your IKEA dresser, the last thing you do is slide a shim under it so that it's level on the old warped floors we have around here. This is the same thing with fields in the brain. You start with a perturbation of your magnetic field that you don't want. So it's a B0 shim challenge. You can generate a compensating shim field that's equal and opposite, add it to the shim, the bad field in the brain, and you end up with a uniform brain in the end, in theory. And so a recent technique for doing this has been to build arrays of loops around the brain that are independently driven with small currents of like 1 ampere, and then synthesize a field of a high spatial order using these 48 independently driven loops to cancel out the unwanted field in the brain. And this is a group at Yale pioneered this, this approach called multi-coil shimming. And I have sort of built on this by looking at their shim arrays and looking at our RF receive arrays and realizing that they share a lot of things in common. So in both RF receive and B0 shimming, you want to place and orient the loops optimally with respect to the region of interest. That means getting them close so you have better RF sensitivity. And if you bring them close, you get more B0 field offset per like ampere of current used per turn of wire, if you want to think of it that way. The shimming is more efficient. And in both approaches, you want to have many degrees of freedom, as many as possible. That improves your parallel imaging performance for RF receive, and it helps you shape the field to match these high spatial order focal B0 hotspots in the brain. You need more degrees of freedom to do that. So why not use the same wire loops to carry the RF and the DC? And so we've done this. We've built so-called AC/DC coils for 3T and 7T applications here at MGH. And in this approach, we use toroidal chokes to bridge RF into, to bridge the DC into the RF loop and out again, and to get it across your RF tuning capacitors. So here, the black components are your RF, and the red components are the DC. And here's what one element looks like with the added DC shim components in the RF receiver array. So we've built this coil on a 3D printed helmet, you can see here. And then we added 6 additional shim elements over the face, which don't receive the RF signal. They just help control the B0 field in the frontal lobes, where we care about it a lot. And this is inside a birdcage transmit coil for 7T. And we drive the currents in these loops using these low-cost, low-voltage, digitally programmable shim amplifiers that we developed, which we've published and released open source. If you want to use them for experiments, the design is available. And we've been using these now in a 32-channel amplifier array for our shimming applications. This is what the whole system looks like, with an offline laptop used for shim optimization, and then a microcontroller connected to the amplifiers via fiber optic to update the shims inside the magnet room. By operating them inside the magnet room, we reduce the amount of cabling and filtering needed, because we have independent wires going to all the channels in the array. So the question then is, does this affect the RF performance of the coil? And we were very pleased that we found only minimal changes in SNR and noise correlation matrices. And we actually found equivalent G-factor performance for a reference coil and then our coil with the shims added. And we're still able to get really nice T2 star images with our so-called AC/DC coil at 7T, such as this one shown here. So then the question turns to, what can you do for shimming with this coil? And here we wanted to figure out, how much current to use in each loop and how much current to use total, and where is sort of the sweet spot, the knee in the curve, where you want to operate. And we found that if you continue to increase the current limit, you do get a little bit better performance, but it's not really practical to continuously increase the amount of current. You get heating, and the amplifiers can't really source that much current. So we're operating them at 3.5 amps per channel, 40 amps total, where we felt you get a pretty good boost in both global shimming and especially what we call slice optimized shimming, where you update the shims on a slice by slice basis. In this case, we've gotten the standard deviation of the B0 over the brain almost down to what you would expect at 3T. So you start out above 50 hertz for your standard deviation. At 3T, the inhomogeneity would be in the low 20s, and you can see that we're not quite there. We're in the high 20s, but it's a big improvement compared to what you normally have with global second order shimming at 7T. So here's some in vivo data showing the baseline second order shim, and then our predicted and acquired multi-coil shim field maps, where we update the shims on a slice by slice basis. And this reduces the distortion in an EPI acquisition, as you can see here. We're showing AP and PA phase encode directions so that the distortion is going to flip between the direction of the distortion will flip, so you can kind of see how much better it's getting. And then we also did TSNR maps just to make sure that updating the shims doesn't compromise the TSNR of the coil, because that's important for fMRI. And if you animate the PA and AP direction, you can kind of see improvements here at the level of the cerebellum, and then in the anterior temporal areas, there's a pretty good improvement, and also in the frontal lobes, there's definitely an improvement in distortion. Still not perfect, but remember, we're going to use the B0 shimming with an increased channel count receiver array and a high performance gradient to get multiplicative gains from all three together. That's our approach. And so in addition to slice by slice shimming, we've also showed you can do multi-band shimming, where you do an optimal shim across 2 slices at the same time. This is work with Cowan, Setz, and Pop's group. And it's actually a 3T example, but the same thing would work at 7T. You acquire 2 slices at the same time, you shim them both using field distribution that looks like this, And you get almost as good performance as if you only shim one slice at a time. And the reason that works is that you have independent rows of coils around the two slices, so you can shape the field in the two slices and still get good dynamic shim performance. Of course, if you go to multiband 3, 4, or 5, the performance would revert back to that of global shimming, which would still be better than your baseline, but not as good as slice by slice shimming. And we've been applying this to ultra high resolution diffusion imaging, including sub-millimeter 600 micron whole brain diffusion imaging, where we use techniques like Buddha to remove all the distortion in the EPI by using 2 shots and then stitching them together with a physics-based machine learning approach to remove any shot-to-shot phase variations. It's a very cool technique. And you might say, well, if you're doing distortion-free EPI, why do you care about the shimming? The reason is that the Buddha problem still does an image reconstruction, and that image reconstruction has a condition number that depends on the B0. And so the condition number, you could think of it as a G factor map for the Buddha. And in this case, the condition number gets better as we apply the dynamic shims. So here we show a baseline and then our dynamic shim case, and at right would be the upper bound or the perfect shim condition number. And you could see the G average is 1.27. We're not quite down to 1.2, but we've made the recon easier for Buddha. So it's analogous to the way that receiver arrays improve the G factor in a conventional sensor grappa recon. Here, the shims help the Buddha recon. And the results are some, I think, pretty impressive diffusion tensor maps shown here at the gray-white interface at 600 micron. You really see the curving fibers going from the gray matter into white matter. So you can really start to study brain architecture at a finer spatial scale. And this is really only possible when you combine high channel count arrays with these new acquisition methods and better B0 shimming. So we've also been applying dynamic shimming to primate imaging. We worked with Anna Rowe's group in China to do some 7T macaque imaging and showing an example of an ECDC coil with 16 channels that we built for them. And they were able to also do multi-slice optimized multi-coil shimming to reduce distortion compared to a baseline case. And so I focused so far on what we can do with local field control for B0 shimming, mostly with an emphasis on EPI for diffusion or for functional imaging. But can we treat this array of coils as a Swiss Army knife that's useful for other applications as well, where improved homogeneity or other shaping of the local magnetic field helps you? And so we've been exploring some of these potential applications, including MR spectroscopic imaging. This is actually quite a natural application for improved shimming with the AC/DC coil because it improves your line width quite dramatically, as you can see here for a CSI slab. That's sort of a slam dunk case where improved homogeneity benefits your ability to quantify metabolites for brain spectroscopy, for example. But it's not only improving the line width that you can do, you can also improve your lipid suppression by using shaped higher order field shapes. And so this is work with Ovidiu Andronesi and Alfred Edelsteinson, where we said, here's an MRSI acquisition where you have a lipid suppression pulse at the beginning, then your water suppression and your acquisition with your spatial encoding. You want to apply a homogeneity shim during water suppression and the spatial encoding. But what about during the lipid suppression? What if you dynamically switch the field shape to have a different spatial profile that actually improves the spectral separation between water and fat on a spatially resolved basis? So you know that most of the fat is in the scalp, and you know that you could shape the field so you have this sort of pattern that is lower at the periphery, higher at the center. And this actually, if you look at the histogram of your metabolites and your lipids, if you spread them out more, your lipid inversion pulse has a wider separation to work with. So it makes the job of the lipid suppression pulse easier compared to the baseline case at the right, where there's a lot of overlap between those histograms, and you're always going to either invert some water or have incomplete lipid suppression. So we've tested this, and if I toggle back and forth between these two shims, you see that the tails on the lipids are improved, and it really reduces the number of spins overlapping in the transition band of your lipid suppression pulse. So this has worked, and we've gotten improved lipid suppression here, showing an area in the back of the head where the lipid contamination goes down compared to the baseline case. And so in addition to lipid suppression, are there other cool things we can do with shaped magnetic fields? And yes, there are. We've started exploring some of these, including zoomed imaging. And the motivation for zoomed imaging, again, is to push the resolution for functional MRI. And so if you push your resolution, you're always going to have more spatial encoding burden for your gradients. And you can try to use a stronger gradient coil, but another way to get around this is to use reduced field of view imaging. And by encoding only part of the field of view, you can get this higher resolution and the same acquisition time. And there's different ways of doing this with fancy RF pulses, but a lot of them involve using longer or higher SAR RF pulses, which is an issue at 7T. So what we've been trying to do instead is tailor the shape of the local B0 field so that you spectrally separate the region of interest, here the occipital lobe in the primary visual area, so that you can do a spatially tailored shim that allows you to only excite that region of interest. And here's just an example spatially tailored shim here. And so the way we do this is take a 3D EPI sequence, because this doesn't work for 2D, and we turn off the partition or slice select gradient, and we replace it with our multi-coil shims. So we play an excitation and then a rewinder lobe, just as you would for your slab select. And so during the acquisition, you flip the polarity of the shim for the rewinder, and then during your readout, you can apply a homogeneity shim, just as you would normally. And if you take the 3D EPI volume, which would initially look like this, and you do a zoomed excitation, this shows the spatially selective images that you would get, and there's very minimal fold over and aliasing from the rest of the field of view here. And so this is done without grappa. And so the payoff for that is, if you compare to a rate 4 grappa that would allow you to acquire the same resolution and the reduced field of view, we see improved TSNR within our primary visual cortex area of interest, about a 20% gain. And when we do fMRI with this, it translates into improved SNR. So there is a region here at the transition to the rest of the brain where we actually have lower TSNR, and that's because there's a transition band in our RF pulse. So in the future, we could try to design pulses with a sharper transition band so that the pass band to stop band transition is sharper. So there's room for more work on this. But we've done some flashing checkerboard experiments and seen that with this zoomed imaging, we get a little bit more conspicuous and a little bit more robust activity in the gray matter, as you can see here in the cortical surface. So can we do other cool things with spatially selective acquisition? We've only begun to explore this, but you can do a peripheral cerebrum excitation, like the one we've shown here, where you're suppressing signal from the center of the head. And why would we care about this? Well, one reason might be to reduce noise from the ventricles because of pulsation and other artifacts that arise due to flow of fluid in the ventricles. This might be helpful if you want to reduce physiological noise, for example. Okay, so another application we're looking at is supplementary spatial encoding for accelerated imaging. And here, what we're doing is building a new shim amplifier that can actually play out arbitrary waveforms on every channel instead of just constant, staircase waveforms between different parts of your sequence. And this will even let us play out arbitrary waveforms during readout, like a ramp or a sine wave. And we do this by using a red pitaya device to drive these shim channels in real time when we're triggered by the scanner. So the spatial encoding experiment, this is another collaboration with Colin Setzenpop and Thomas Witzel. We're adding a small modulation to a wave readout to spatial encode with a higher frequency than you can achieve using the scanner gradients. So we call it multi-frequency wave because we're using the AC/DC coil to add this extra high frequency encoding on top of a wave readout along one or more dimensions, Y and Z. To improve voxel spreading and parallel imaging performance. So it's complementary spatial encoding. And so here's what the wave voxel spreading looks like along the readout direction. And with the multi-frequency wave, this is a simulation showing that you can improve voxel spreading, which might improve the G factor for your acquisition. And so that's actually an acquired, so that was actually our coil inside the bore, and we were actually driving multi-frequency wave signals on the RF coil. So the RF coil is being used for spatial encoding, and that most of the noise you were hearing was coming from the RF coil itself. So kind of weird concept, right? We're using the RF coil to do spatial encoding. What does this actually work? And actually, yes, we're getting some images just in the last few months showing that the multi-frequency wave images actually work, and we are getting improvements in the G factor compared to the baseline case. This is still a relatively weak encoding field. So with a better, coil, we might be able to get stronger encoding fields, but we're just doing proof of concept at this point. And we've worked really hard to reduce the EMI from the new electronics that's operating in the scanner room. We still have a little bit like the zipper artifact, but we've dramatically improved the noise floor through better shielding and better design of our RF traces in the electronics. So we've also been working on calibrating the experiment. It's complicated because you now have time varying waveforms on every shim channel in the AC/DC coil, but using a chemical shift imaging or point spread function mapping approach here shown at bottom, we've reduced almost all of the artifacts in the image, and it looks pretty crisp compared to the ground truth. And if you compare it to the wave image that was fourfold undersampled, we get less RMSE compared to the conventional wave. So there is some added spatial encoding happening. All right, so on to our next application. The next one I want to talk about is arterial spin labeling. So without going into the details of ASL, I just want to point out that one of the confounds in ASL is intersubject variability in B0 within the labeling plane and the brain. And one remaining challenge is to do territory mapping in ASL. So you can map perfusion from individual vessels to different parts of the brain. So we've tried to improve ASL by building a shim coil that fits around the neck and generates independent shim fields that you can then use for ASL experiments. This is what the prototype looks like. It slides into a Siemens 32-channel head coil. I'm going to speed up a little bit because I'm running late. But we basically turn on a shim field during the labeling in a P-Castle ASL acquisition, and then turn off the shims for the other modules of the acquisition. It uses a spiral readout in this case. And what we do is spectrally separate one of the vessels. Here I'm showing the right carotid vessel being spectrally separated from the vertebrals and the other carotid. And what that lets you do is label only one artery at a time. Here we're showing a shim field that does spectrally separates the other carotid. And then here we're showing one that separates the vertebrals. And now you have histograms for the spins in the different compartments that allow you to only label one or the other vessels. And so this is our first in vivo result showing that we can do territory mapping from the two carotids in the vertebral circulation and get territory maps. Now there's other ways of doing this, just using RF and linear gradients, but we wanted to show proof of concept that local field control provides another tool for territory mapping that's potentially simpler on the pulse sequence side, but requires additional hardware. So the final Swiss sort of blade in the Swiss Army knife is to use TMS arrays for local field control. And this is the final part of my talk. And so I wanted to talk about TMS, especially because I know there's interest at Sunnybrook and by Fashwan and others. What we're interested in doing is concurrent TMS-fMRI. So TMS, of course, uses probes placed close to the body to generate electric fields using very short pulses of current and depolarize neurons in the cortex. And one thing you can do is concurrent TMS with fMRI to see how that stimulation of the cortex changes the bold activity across the whole brain. And one of the challenges of this approach is that you have to manually position the probe in the scanner. You can't really move the stimulus during your fMRI experiment. And you may have a trade-off in sensitivity and coverage, because here you're using a loose fitting volume RF coil, which won't be good for fMRI. So there have been improvements on both of these fronts recently on improving the steerability of TMS using multi-channel TMS to dynamically steer the hotspot across the cortex and to change the E-field orientation. With Apo Newman-Ma's group at MGH, they're using 3-axis TMS coils, where you can now shape the field by using these 3 axes independently, and then have 16 of these 3-axis coils across the head, have 48 channels in total. This is a rendering of what their TMS, multi-channel TMS concept looks like inside the MRI scanner to allow you to steer the stimulus during the fMRI experiment. So the benefit of this, like I said, you have many more degrees of freedom to shape the field. And these could be useful as sources for magnetic fields as well inside the brain for spatial encoding and shimming. And so instead of using the E field, we would use the B field. They're low inductance, so you can drive them with low voltage, inexpensive shim amplifiers. And because they're so close to the brain, you're getting a very strong B field gradient, which is why they're so enticing for spatial encoding applications. And another advantage is that you're positioning these over parts of the head that have very few nerves that could be stimulated by conventional gradient coils, which means PNS thresholds may be higher for these coils, allowing you to potentially go to higher slew rates compared to a conventional gradient. So we've done now some preliminary experiments that I'll show where we use dummy TMS coils for spatial encoding. And to enable this work, we've been using a special RF receiver array in purple here, developed by Lucia Navarro, that has ports where you can slide the TMS onto the scalp. And there are 28 RF receiver arrays in this loop array, which were designed to be compatible with the TMS and allow safe use inside the scanner with minimal compromise of RF sensitivity. And so we've done some simulations of what you gain by using TMS for spatial encoding. And in fact, compared to the 32-channel array I showed earlier, simulations suggest that the 48-channel TMS coil would perform even better because you have more degrees of freedom. There's more turns of wire, so you get more B field per amp of current. You can generate stronger fields, translates to better field homogeneity. Here's the experimental setup on a 3 Tesla scanner with shim amplifiers connected to the 16 Z coils in the array. And what we were able to do with this experimental setup was dynamically shim a head phantom that had an air inclusion in the sinus area, simulating the off resonance of an actual brain. And dynamic slice optimized shimming was able to improve the homogeneity of the field inside this phantom. Next, we implemented dynamic shim updating to null the B0 field inside a phantom on a slice-by-slice basis. Here we toggle AP and PA phase-encoded EPI slices to show a modest reduction in geometric distortion from the dynamic shimming. Good temporal stability was observed and no image artifacts were seen to result from the current switching. These B0 maps show an X-gradient field offset of 250 microtesla per meter, which was used as a shim challenge for the 16-channel TMS array. Using only 3.5 amps of current, the array was able to null the field over a 4-centimeter slab on an anthropomorphic head phantom. Sorry, I recorded my voice for a different talk on those slides and I forgot to take out the narration. So, so you can see we're able to shim with these coils, which I think is really exciting because it's synergistic with our goal of doing fMRI for multi-channel TMS studies, because we want to reduce distortion and signal voids in the EPI for the fMRI. So we're now, potentially going to be able to use the same loop array for this brain stimulation and for local B0 shimming. But there's even more we can do with these coils because they're so close to the head and they have multiple turns. You actually can generate quite powerful gradients inside the brain to use for spatial encoding, not just B0 shimming. Here are simulations of the gradients you get with the X, Y, and Z coils in that 3-axis array, showing that they create gradients along different directions. And if you were to scale up the available current to 100 amps, you could generate 100 millitesla meter gradients across cortex, which is quite a powerful gradient field, easily strong enough for most imaging experiments. And a conventional clinical scanner is only 40 millitesla per meter, to put it in perspective. And you could even generate crazy gradients like this quadrupolar field, which has been used for methods like Patlock, which Foshwan has also worked on, for nonlinear gradient encoding. So you're not limited to linear field shapes. So by shining the light where you need it, you could even do things like diffusion encoding in the gray matter. You could generate a spatially varying B-value map, such as the one I'm showing here. This was actually experimental data that we acquired on a phantom using one TMS, dummy TMS element placed on the phantom. And we showed that we could get B-values of up to 500 at the level of gray matter, just using 4 amperes of current. So 500 is already a significant B-value for routine diffusion imaging. If you ramp this up from 4 to 200 amps, in theory, you could get over 1 Tesla per meter gradients at the level of gray matter. You're never going to be able to achieve that over the whole brain, but if you're interested in studying the microstructure of gray matter, this enables microstructural diffusion MRI with a whole new spatial scale. So this is showing simulations of how small the structures are you could resolve with the diffusion imaging, comparing Human Connectome Project 1 and 2 with this TMS array that could achieve up to 2 Tesla per meter in the cortex, also with a very high slew rate. And so Human Connectome 2, which is still being built at Siemens, could resolve maybe 6 to 7 micron structures. Whereas if you have this stronger gradient in the gray matter, you could go potentially below 4 micron. And that's relevant because it's at the spatial scale of soma and neurite structures in the gray matter, as well as axonal projections from the gray matter that you might want to study to see how their size and density varies in different parts of the cortex, let's say primary motor versus somatosensory. How does their microstructure differ? You could begin to structure this study these structures in vivo in the gray matter, which is pretty exciting. So to recap the whole talk really briefly, increased field strength at 7 Tesla and beyond opens up new opportunities for high resolution neuroimaging. But I would argue only when these higher field magnets are paired with next generation array coils. And by pushing the channel count from 32 up to 128, we really think that we'll have better sensitivity and better accelerated imaging performance for fMRI at 7T, which we're going to need to break the 1 millimeter resolution barrier. As we push these channel counts, I hope that we can also use our multi-coil arrays for B0 shimming and other local field control applications which reduce artifacts and enable new applications in MRI. And if we have multiple degrees of freedom, not only can we do better TMS with them by steering the E field dynamically over the cortex, but maybe these same arrays could do double duty for encoding and shimming applications as well. And so with that, I'll close. I'm sorry I went so long, but I look forward to questions and discussions on any of these topics I've discussed. Thanks so much for your attention.
Thank you, Jason.